All right, Bismillahirrahmanirrahim. Now I'll start with small signal equivalent circuit for the MOS transistor. So if we have an NMOS transistor, this is the source, gate, drain, and the gate. Usually we say that the bulk is connected to the source. So the equivalent circuit will be open circuit here, right? This is the source, this is the gate. Since there is no current here, okay, the volt between this point is from the gate to the source is VGS, and this will be GM VGS. This is the drain. So you can see this is more or less like the VGT, except this here is open circuit. It was RBI in the VGT. We don't have RBI because there is no current here. Huh? We don't have anything connected between the gate and the source, unless we have a connection here. So this is the basic model. If we have a resistance RO, then we should include it. So RO will be part of the transistor. So you can see it before the drain, this RO. So this is basically the model here, okay? Now, GM, we can find it from the DC analysis. So GM is equal to square root of 2K dash W over L times ID. So if you know ID, how we got this, I'll show later on. We know ID, right? We know K dash W over L, we can tell what is GM. So the GM for us is known now, okay? So that is the only parameter here. In BGT we have R by R8 based on the model. Here we have only to find GM from the DC analysis. But again, from the DC analysis, we have to find what is IDQ and the DSQ. This is your operating point, which is the point where we have to operate our transistor in saturation so that it can be used as an amplifier. Let's say we work here, so this is your Q point, IDQ and VDSQ, okay? Right, again we have three types of amplifiers. We have what we call common source amplifier, and same as we have done with the BGT, in common source, we'll start with this basic model, basic configuration, basic common source amplifier, where we have, let's say we have, this is the biasing circuit, RG1, RG2, and we have to use now, this is VDD, we have to use coupling capacitor C1, and that is your input VI here to ground, and then we have to use another coupling to couple the load, and RL, V out, and this is your RD. So this is a basic common source amplifier. We would like to find the gain, expression for the gain, input resistance and output resistance. As I said before, the input resistance is the resistance seen after the source, and the output resistance is the resistance seen before the load. So your transistor is this. So we have three nodes here. This is the gate, drain, and source. Okay. So we can just replace now the transistor with its equivalent model. Okay, so this is VGS, source, drain, gate. Okay, so the source is grounded, just be connected to the ground here, and the gate, we have two resistors in parallel, RG1 and RG2, so we can call it RG. Okay, and then the capacitor is shorted out, and we have here what we call we have our input, which is VI here, and from the drain we have a resistor RD and the load RL, and that is V out here. This one is GMVGS, and as I said, GM is already known to us. Now the input resistance is the resistance seen after the source, The output resistance is the resistance seen before the loop. Now what you can see here, Rn, to find Rn, is nothing except Rg here. ولهذا we use big values here so that we keep the input resistance of the MOS high. And to find R out, set the input to 0, so this will be shorted out, right? So if we short out this is 0, VGS is 0, so this is open circuit, and we have R out equal to RD. Now finally we have to find the gain. Also forget about this now. So we have to find the gain now. I can combine these two resistors, I call them RL dash as we've done before. So we can say V out is equal to, this current is ID, right? V out equal to minus ID into RL dash equal to minus GM VGS, because it is the same, right? Multiplied by RL dash, and this is my equation number 1. What is VGS in terms of VI? VGS equal to VI, so VGS equal to VI, that's equation 2. If we sub 2 in 1, then we can find the gain. AV equal to V out over VI equal to minus GM RL dash. So this is the gain of the amplifier. As you can see, we can control it using GM, and GM can be controlled using the drain current ID, the dimensions here, but there are some consequences. You have to be careful about this, right? So this is the basic amplifier, basic common emitter amplifier. Now let's modify this circuit a little bit, okay? And let us assume our source is not ideal, so it has RS. So our source here has RS. But this will not affect our DC point, okay? DC operating point, it will not affect because it has nothing to do with it. DC point is only on this portion of the circuit. So if we have RS, now my circuit will be modified a little bit. Small signal equivalent circuit. This is the source here, gate. So from the source is grounded. The gate, we have two resistors now. RG, this is the equivalent of the two, right? RG1 and parallel with RG, because this will be grounded, this is grounded, they are in parallel. Then we have RS here. And the source is here, VI. From the drain, so this is VGS. Huh? From the drain side, we have RD, RL, and that will be our V out here. So let's start with the gain first, GMVGS. Now as you can see, adding RS will not affect RN, and it will not affect R out, because it will be the same. Huh? So just this is Rn, this is R out, right? So Rn is Rg, so it is the same, because the source resistance is not part of the input resistance, it is part of the source. And R out will be the same. We short this, if we short this, this will be shorted out. The volt here is 0, VGS is 0, this will go out, and we have R out equal to RD, okay? Now to find the gain, here will be the difference a little difference. V out is equal to minus GM VGS times RL dash. So this is equation number 1, which is the same as the previous one, right? So I call this RL dash. Now what is VGS? It is not VI anymore because we have now RS here. So VGS will be, we can find it using the voltage divider. So we can say VGS is equal to VI times RG over RS plus RG. And that will be our equation number 2. So if we sub 2 in 1, to get. V out is equal to VGS minus VI RG over RS plus RD times GM RL dash. GM RL dash. If we divide V out over VI, that is the gain, which is minus RG over RS plus RG into GM RL dash. So adding RS will add this term to the gain on here. So we can see here, it will reduce it a little bit. Lakin, since we have RG1 and RG2 large mega ohm, RS can be okay, so it will have no effect. Even if we add RS, the effect will be very small. Lakin, if you want to be precise, then you have to include RS in your analysis. So that's the first type, okay? Now let's say we add a resistance here, which is RS, okay? So I'll call this R seg now, or I just remove it, so you know its effect, okay? So I remove it, that's just to, not to confuse you with RS here. So if this is my circuit now, huh? So now, I can use T model, or I can use bi model, it is up to me, right? So I'll do it in both ways. Now if I want to draw the small signal equivalent using bi model, it will be source, drain, gate here. This is VGS. From here we have the gate, resistance RG, the equivalent of the two, RG. And then we have the source, that is VI here. From the source we have a resistance RS to ground. And from the drain side, we have the same thing, RD, and RL. Okay? This is your V out now. This current source is GMVGS. Okay? Now here you have to be careful, because VGS is not VI anymore. VGS is not VI anymore. It has something here. It is the gate potential minus the source potential. So if we call this point is VG, then this point is VS. VGS will be this minus this. So this is very important. Like from the input resistance and output resistance point of view, we have Rn here, R out there, right? So Rn is equal to R. So it is the same. Now to find RD, R out, we short this. So if we short this, this potential will be minus Vs here. Minus Vs is GMVGS here. So again, we can see that we can approximate it as if this potential is 0, this node is 0, this volt here will be not activated anymore, so we don't have any supply for this. This will be open circuit, and we have R out is equal to RD. To find the gain, we have to be careful now. If I call this RL dash, then we have V out is equal to minus, this is ID, minus ID RL dash equal to minus GM VGS times RL dash. And this is your equation number 1. What is VGS? You cannot say VG equal to V. Be careful. كان في مقاومة هنا وما كان في مقاومة هنا. If there is a resistor RS or not, VGS is not the same as VI because we have something here now. So we can say to find VGS, VGS is equal to VI minus VS equal to, so VG minus VS. VG what is VI? So this is VI minus VS equal to VI minus the current multiplied by the resistance, which is GMVGS times RS. So this is VGS. So if we rearrange, we can say VGS is equal to VI minus GM VGS multiplied by RS. We can take this to the other side. So VGS plus GM VGS RS equal to VI, or VGS 1 plus GM RS equal to VI, or VGS equal to VI over 1 plus GM RS. So this is my equation number 2. So we can see here the effect of RS. لو كانت RS مش موجودة, this becomes 0 and VGS equal to VI. لكن since it is there, it means it will degrade our gain, to reduce the gain. So if we sub 2 in 1 to get V out equal to minus VGS, which is this VI over 1 plus GM RS times GM RL dash. So the gain V is V out over VI equal to GM minus GM RL dash over 1 plus GM RS. So you can see without RS this is the gain, with RS this is the gain, so RS will decrease the gain. Okay. Now, effect of RS here, it will stabilize the bias point again, because if there is a variation in VDD, this will act as a negative feedback and it will reduce this fault, VGS. So that is one. The second one, it will increase the input range for VI, so we can increase VI. Instead of 5 milli, 10 milli, we can go more than that. Lacking the input resistance will remain unchanged, so there is no reflection here because there is no current. Okay, so the input resistance will be the same there. So it will reduce the gain. It will stabilize the bias point. It will reduce the gain. It will not. It will increase the input range. Okay, but it will not affect the input resistance here. So this is for the common emitter amplifier with RS. Now, if I want to increase the gain, just stabilize the bias point, increase the gain, then you can just simply add a capacitor here. So the capacitor, the bypass capacitor, will short RS in AC analysis. It will keep it in DC, but in AC analysis it will short it out, and we'll have the gain the same as the previous one. Okay, so that is for the common emitter amplifier. The common source, sorry, common source. The second amplifier is the common gate amplifier. Common gate amplifier. Okay, just have to check the video if it is okay or not. Okay, so the common gate amplifier, the gate should be common to both input and output. So we can just ground it here. Then we can bias this using bias current coupling here. We can add RS here, there is no problem. This is the input VI or VS, and we can take the output from the collector. So this is DDD, coupling RL, and that is V out RB. Okay. So if we know the parameters, we know K dash W over L, then the bias current here I, so the DC circuit will be like this. This is open circuit, so we have the current I equal to IS. So I equal to IS equal to ID. So if we know ID, then we can say GN equal to square root of 2K dash W over L times ID. We know this parameter, we can find here. Okay? Now for the AC circuit, we have to short any DC source or make it open. If it is current source, we activate the DC source. If it is voltage source, we make it 0. If it is current source, we make it short. So my AC circuit will be something like this. We have, this is RD, the transistor. The current source here will be open circuit. The coupling here is shorted out. RS and this is your input VI, okay? Ground. The gate is grounded, the coupling here is shorted out, and we have here RL, and that is the out. Right, we can use now T model for this. So, because the source is not grounded, and in T model it is simple. So you have this is your resistance, we call it 1 over Gm. This is the gate, this is the source, and this is the drain. And we can call this GMVVE, okay, sorry, GMVGS, okay, or we can simply say it is ID, okay. And VGS is this fault between the gate and the source. Now if we connect the source, we'll connect it to RS and the voltage source, which is the input signal. The gate is grounded. From the drain, we have RD and RL, and that is V out here. The current here is ID also, because there is no current here, ID equal to 0. So it is like open circuit from this side. Now the input resistance is the resistance seen after the source, because RS is part of the source, so that is Rm. And the output resistance is the resistance seen before the load, so that is R out here. Okay. All right, so here we can simply find the input resistance. So what is Rn from here? You can see Rn from here to ground. You can see only 1 over Gm. So Rn equal to 1 over Gm, and you know Gm. Then that's it. Done. R out, to find R out, set the input to 0. If this input is 0, the current ID will be 0. This will be open circuit, and R out equal to RD. R out equal to RD. So we have the two things here. Now to find the gain, I will combine these two, call them RL dash. So we can say V out equal to minus ID times RL dash. That's question 2. Now ID is this current. So I don't need to use GMVGS. I can, but since I have ID here, I can find the relation between VI and ID very easily. So I can find VGS also in terms of VI using a voltage divider, or I can find ID using just Ohm's law V over R, because these two resistors to ground are in series with the volts, so I can find ID, which is minus VI divided by RS plus 1 over Gm. So you can say ID is equal to minus VI over RS plus 1 over Gm is equal to, لو أخذنا Gm عامل مشترك, so it is VI Gm divided by 1 plus Gm RS. And that's equation number 2. Now if we sub 2 in 1, sub 2 in 1 to get V out is equal to minus will cancel, so we have VI Gm 1 plus Gm RS multiplied by RL dash, so the gain is V out over VI is equal to Gm RL dash 1 plus Gm RS. So this is the gain for the common gate amplifier. Now, one comment here is that Rn is 1 over Gm, which is small resistance actually, right? Because Gm can be 40 milli or so that is small resistance. So in this case, you can use this type of amplifiers as current amplifier or current amplifiers, because they're even current maybe can be used as a current amplifier, right? Because the input resistance is small, 1 over Gm, right? Right. And finally, we'll have the common collector amplifier. Common collector. So in common collector, we have circuit shown here. Let's say this is RS, then this is the load, RL, V out, VGD here, and we have the input here. Let's say we have the passing already given to us, or it is already done, you know, so it is already biased in active mode, in saturation mode. So this is the circuit for one circuit of the common collector amplifier. Now we want to do the same thing, find the gain, input resistance and output resistance. So again, since the source is not grounded, we can use the T model. So this is the T model here. So we have, this is ID, this resistance is 1 over GM, okay? And this is the source, this is the gate. The current here is equal to 0, be careful, huh? And this is the drain here. So the source is connected to RS and the load, RL. And this is V out. And the gate is connected to RJ gate and the input VI. From the drain, it is grounded. So in this case, we can include the output resistance RO, because we want to see if this is buffer, even though if we include RO, it will be also a buffer, because the buffer characteristic, the output resistance should be small, right? So this resistance here, we can turn it down, okay, as we have done with the BGT, so we can connect it here as R1. Now the input resistance is this, Rn, the output resistance is here, R out, okay, R out. Remember, the gate current is 0, so what we can see here is open circuit, there's nothing there. So Rn is Rg. Why? Because the resistance here is infinity. Volt divided by current, the current is 0, so it is infinity. So we cannot see anything here. Infinite input resistance in this direction. So the input resistance of this amplifier is Rg only. Now to find the output resistance, we have to short this. So we short the input. Okay? Now if we ground this, this will be grounded. So this node is grounded. Okay? So that is your circuit now to find R out. Now what you can see from here to ground, you can see 1 over GM in parallel with RS and RO. So we can say R out is equal to 1 over GM parallel with RO parallel with RS. And this is almost 1 over GM because it is the smallest one. Okay? So it is small resistance. Now we'll go back to the gain. RG here, and this is your VI. Again, as I said, you can add RS here and do the analysis. So to find the gain, we'll forget about this now, R out. The current here is ID. I can combine all this and call them RL dash. So we can say, as you can see now, V out will be the current ID multiplied by the barrel equivalent of this resistor. So V out is equal to ID times RL dash, that's equation 1, where RL dash is equal to RS barrel with RO barrel with RL. Alright? That is V out. Now, what is ID? ID is VI divided by the sum of the resistances. So ID is equal to VI divided by 1 over GM plus RL dash equal to VI GM over 1 plus GM RL dash. So that is equation number 2. Sub 2 in 1 to get V out is equal to ID, which is this, VI GM over 1 plus GM RL dash multiplied by RL dash. The gain AB will be V out over VI. It is GM over GM RL dash over 1 plus GM RL dash. Now this GM RL dash is much greater than 1, so we can remove it, and we have GM RL dash over GM RL dash is equal to 1. Now, as you know, the buffer characteristic, the gain should be unity, the output, the input resistance should be high, RG is high, ولهذا نحط احنا 10 make. R out should be small, it is 1 over GM, and that satisfies the buffer characteristic. That's enough for today. Assalamu alaikum wa rahmatullah.